Hello students, good evening all. So welcome back to our next session of chapter Binomial Theorem. So we have already finished 3 sessions in this chapter of Binomial Theorem. So today this will be our last session, so where we are going to focus on the application part of this Binomial Theorem. Right, so meanwhile remaining students can join the session. We'll just have a quick overview of the concepts that we have covered in our last session of Binomial Theorem. Along with that, what are the things that we are going to cover in our today's session of Binomial Theorem. So I had a bit cold guys, so please bear with it. So yeah. So as I mentioned in our last session, we mostly talked about these terms which are related to binomial theorem, like a general term, a middle term, and a particular term, as well as the term from the end of the expansion. Right. So in our entire session of binomial theorem, like our entire last session, so it's completely dealing with the terms. So it's entirely dealing with the terms which are related to binomial expansion. So the first one which we have discussed is a general term as well as the middle term in the binomial expansion. So we know the general term is represented as TR plus 1, that is R plus 1th term here will be equal to NCR x power n minus R a power R. Right, so this is our standard representation of any general term, like it's a general term for an expansion x plus a whole power n. Right, so when it's come to middle terms, so middle terms actually depends upon the number of terms. So if we have some odd number of total terms, then the middle term will be only one term. Whereas if we are having total number of terms which are even, so if we are having even number of total terms, then there will be two middle terms in that particular case. So when we talk about middle term, if n plus 1 is odd, so here you have to understand it's not n plus 1 should be odd, then the middle term will be n plus 2 by 2 term. Whereas if we have n plus 1 equal to even, then we'll be having, because here even number of terms, so we'll be having two middle terms which are given by n plus 1 by 2th term and n plus 3 by 2th term. So these are the two terms which are the middle terms when we have even number of terms in a binomial expansion. Right guys? So after this general term as well as the middle term, then we have discussed a special case, that is determining a particular term. So it can be any particular term. So basically we can use our general term also, and it depends upon the expansion. If it's given according to the particular expansion, then we can directly apply this particular term method, which will be easiest when compared to our general term in binomial expansion. So for a particular term, what will be the expansion guys here? X power alpha plus, it can be plus or minus 1 by x power beta whole power n. So here we are not considering the coefficients here, so we are only considering this x powers and all. So this is given by n alpha minus r into alpha plus beta will be equal to m, where m is the power of the x which we are trying to find out. Right. So if we want to find the independent term, like the term which is independent of x, then our m value here will become 0. Then that particular term is given by n alpha minus r into alpha plus beta is equal to 0, which states that r will be equal to n alpha by alpha plus beta. So once we predict the r value, then it will be easy to find out that particular term. Right. Once we figure out the r value, then we can go by our general term and we can find the particular term there. Right, so you can go by general term also, you can go by this particular term determination, so anything will be fine. But if the expansion is in standard this form, then it will be easy to go by. It's like it will be easy to find out the R value when compared to applying this general term in binomial expansion. Right, guys? So the next term here is find a term from end of a expansion. So here we are talking about this end of the expansion. That means if we are having tr plus 1 from the end, that will be equal to tn minus r plus 1 from the beginning. So this is the relation between our terms from end of the expansion as well as the terms from the beginning of the expansion. So using this particular condition, we can directly end up finding whatever the term which is required to find out the term from the end of the expansion. Right, so these are the all things which are related to our terms, which we have already discussed in our previous session of binomial theorem. So now what are the concepts that we are going to cover in today's session? So the first one is nothing but application part of our binomial theorem. So far we have seen the expansion of it, how to figure out the terms related to binomial expansion and so on, everything. Right, so now we are completely done with the things which are related to binomial theorem. So now we are entering into the applications part of this binomial theorem. So here in this applications, we are having different concepts like divisibility test, finding the remainder, we can say, finding the last digits, we can say, or relation between any two given number. So there are lots of applications here of binomial theorem, and we are going to discuss each of the application of binomial theorem here in our today's session along with some examples. Right, and we are left with one last concept in our binomial theorem, which is nothing but the multinomial theorem. So now I know you guys are familiar with this multinomial theorem, which we have already learned in our permutations and combinations. So you guys are already having a brief idea regarding this multinomial theorem. Right, so yeah, so these are the two concepts which are left over in our entire chapter of binomial theorem, so that we are going to cover in our today's session. So the first one will be application part of this binomial theorem, and the second one, there's a small discussion regarding this multinomial theorem. Right, so without any delay, so let's begin our today's session with this concept of applications of binomial theorem. So the first one in our application part of binomial theorem is something to deal with the divisibility test. So I hope you guys are familiar with this divisibility rules for 2, 3, 4, 5, 6, 7 and so on. You 8 and 9 and so on. Then you can have you already familiar with this divisibility rules. Right. So now the question is how it is related to the application part of our binomial theorem. Right. So before getting into that, so let's have a look here. So what is the divisibility rule of 2? The units digit can be 0 or any divisible number, like even number we can say. Even number 0 and the even number on the units place. And for 3, sum of the digits should be divisible by 3. And for 4, the last 2 digits of the number should be divisible by 4. And for 5, the unit digit should be either 0 or 5. And for 6, it should be divisible by both 2 and 3. And for 7, it will be sum of the, we have to check the last digits. And even for 8, it will be the last 3 digits. And 9, sum of the digits. And 10, the units place should be equal to 0. So you guys are familiar with all these divisibility rules, and also there is nothing new here because you have already learned this divisibility rules in your lower sections. So now let's see how this is applicable, like how we are going to apply the concept of binomial theorem here, which is related to the divisibility test. So we'll be understanding, so there is no standard methodology and all here. So we'll just go by the questions related to the divisibility test in order to see the application part of our binomial theorem. So here comes the first one, that is show that 7 power 2n plus 7 is divisible by 8. So here n is any positive integer, and the thing which is given here is 7 power 2n plus 7. That means this is having an exponent, which means this can be rewritten accordingly our binomial terms, and then we can expand it in order to prove that this is divisible by the number 8. Can you guys split and see how we are going to split this, how we are going to do into our binomial identity terms by looking at the question? Can you guys let me know if you guys have any idea? So you have to observe the term which is given here, and you have to observe the number which we have to prove that it is divisible by what number. So here the term which is given here is 7 power 2n plus 7, and we have to prove that this entire term is divisible by 8. That means here our 7 power 2n can be rewritten in terms of 8 or not, right? So that means sorry, 7 power 2n plus 7. So this can be rewritten as, so here 7 can be rewritten as 8 minus 1 whole power 2n plus 7. So now you can see this is in the format of our binomial. So now it is easy for us to expand this. So do the expansion here. So before doing that, you have to have an idea. So when we say something is divisible by 8, so when we have 8 into some k, or we can say some 8 into lambda or some 8 into delta, something like that. It can be any constant. So whatever the k value here, but if we have 8 into that entire term, then we can say that that entire term is divisible by 8. So now here we have to do the same thing. So we have to represent or deduct that in such a way that this entire term is equal to 8 lambda or 8k, something like that. In order to prove that, in order to show that this 7 power 2n plus 7 is divisible by 8 here. So that's the overall hint here. So first thing, we have rewritten 7 in terms of 8. So as here we have to make it divisible by 8. So now do the expansion here. So this can be written as 2n c naught 8 power 2n minus 1 here. So minus 1 power 0, and then it will be minus here because it's a minus. So 2n c1 8 power 2n minus 1. So 1 power 1. So 1 power anything will be 1. So let's leave it. So plus here 2n c2 8 power 2n minus 2 minus 2n c3 8 power 2n minus 3. So there is no need for n. So let's go for the last term. 2n c 2n. So 2n is a multiple of 2. So it will be a even number. So anything power even term will be positive only. So here sign will be plus only. Right. So 8 power 2n, it will be 0. 8 power 0 will be 0. And 1 power 2n will also be 1. So we can leave it like this. So this entire plus we are having 7 here. So this is the expansion here for the term 8 minus 1 power 2n plus 7. So now as we have to prove that it is 8 into something. So now let's expand this, simplify this, and see how can we represent this, whether we can represent this as 8 into something or not. So 2n c naught will be 1 only. So it will be 8 power 2n. Right? And here 2n c1. So it will be as it is, we can leave it, and here 8 power 2n minus 1. And here at last, before term here will be 2n c 2n minus 1 8 power 2n minus 2. That means it will be 8 only. And here it will be minus because it's a negative. So minus 8 2nc 2n, and here 2nc 2n will be 1 plus 7. So this 7 plus 1 is nothing but 8. So now we can rewrite this as, so let me write down here. So 8 power 2n minus 2n c1, 8 power 2n minus 1, and so on. And before term here 2n c, 2n minus 1 into 8 here, plus 7 plus 1, 8 here. So now let's just identify here whether we could take the number 8 common from each of the term in the expansion or not. So here 8 power 2n, which means there will be a 8 here. So we can take 8 common. That means 8 power 2n minus 1. Right? Similarly, we can take something here 8, then it will be 2n c1, 8 power 2n minus 2. Right? And so on. If we go by here the last term will be remaining with 2n c, 2n minus 1, and here also plus 1. So here from each of the term we could be able to take this 8 number common here. Right? That means here we have already taken the 8, and it doesn't matter whatever the entire term which is remain here. So that entire thing we'll just assume it to be k. So now we have represented this entire expansion as 8k, which means the given binomial term, that is 7 power 2n plus 7, it's obviously divisible by 8 because it is coming in the format of 8k, not instead of 8k plus 1, 8k plus 2, something like that. It is 8k. Right? So where k is nothing but it can be any positive integer, so which we have seen in the expansion. So now we have proved that the 7 power 2n plus 7 is nothing but 8k, which means this term 7 power 2n plus 7 is nothing but divisible by the number 8 here. Right? So now I hope you guys are familiar with how to deal with this divisibility test using our binomial theorem. Right? So let's move on to the next question. So here comes one more question. So I hope you guys can give it a try. I'll just give you 2 to 3 minutes. So have a look. Similar way you can do it. So let's have the look over the number which we have to prove, like divisible by what number, and see what is the expansion here which is given. So for this, I hope you guys can give it a try, but at last I'll just give you a hint how to start with it. Then you can, if you are solved it before ahead, then it will be no issue, good enough. If you couldn't able to solve it, I'll just give you some hint in order to give it a try. So here one number is 13, other number is 19, and the other number is 162. So it will be better when we write the expansion term in terms of 1 also, because it will be easy to expand. So think in that point of view and give it a try. So let's rewrite this 13. So 13 can be written as what we can say, the nearest value which is divisible by here will be. So in order to get this 1, how can we write it? So we can either write 14 minus 1 or we can write 12 plus 1. So let's prefer 1 plus. So I'll just write 1 plus 12 whole power 99 minus even 19 also can be written as 1 plus 18 whole power 57. But both of this 12 and 8 are not divisible by this 162. So let's try to convert here in such a way, such a number here we should get such that it should be divisible by this 162. So 12 can be written as 3 into 4, where 3 is divisible by, where 162 is divisible by 3 here. Similarly, 18 can be written as 9 into 2, and again 9 here. So 162 is divisible by 9. So now we have to apply our binomial expansion here. Right, so it's a bit lengthy, but the thing we have to get is, so 2 points we have to keep in mind when we are doing this divisible. So try and write it such a way that we'll be having one number, one term amongst the 2 terms should be 1. So mostly we'll try that way so that it will be easy for us when we are doing the expansion here. Right, so that's why I have followed this way where I could write 1 plus 12 and all. Right, but here 12, 162 is not divisible by 12. Same way 162 is not divisible by 18. But this 12 can be again split and can be written as 3 into 4, as well as 18 can also be splitted and can be written as 9 into 2. Where here 162 is divisible by 3 as well as 162 is divisible by 9. So now we'll just use our expansion for these 2 terms here. That means 99 C0 1 power 99 3 into 4 power 0 plus 99 C1. So 1 power, so we can leave it that. So it will be 3 into 4 power 1. So that's the advantage here. If we write it as 1 term can be directly eliminated here. And then 99 C2 3 into 4 whole square. Whatever the last term. 99 C99 3 into 4 whole power 99. And this entire term should be subtracted from this term. That means minus, I'm just writing down here, 57 C0, again 1, so no need to write, 9 into 2 power 0 plus 57 C1, 9 into 2 whole power 1 plus 57 in C2 into 9 into 2 whole square and so on, plus here guys because there is no minus. So 57 C 57 9 into 2 whole power 57. So this is another expansion. Right. So now we have to rewrite this such a way that we could take 162 common here. So that's the whole idea. So this entire term will be 1. So 1 plus 99 C1 3 into 4. Right. And then 99 C2 3 into 4 whole square. So here we can take the entire term to be a k1. So here you can see 3 into 4 is nothing but 12. So 12 into 99. So when we write here, so it will be 3 power 4 into 2 k1. So I'm just leaving the remaining terms. I'm just taking the remaining terms to be constants here. And same way here, 1 plus 57 c1, 9 into 2, and then 3 into 3 by 4 into 2 k2. Why I'm writing here is this entire term here is nothing but a multiple of 162. Right, so then you can take 162 common and we'll be having this term because 3 power 4 into 2 is nothing but 162. So that is the only reason why I have represented it in this manner. Right, but you can do this further simplification. There is no issue here. But the first and foremost thing here you have to identify is the figure out what is the first step. That is the most crucial part here. So if once we have figured out the first initial step, then the next one will be a simply expansion here. Right, so the next you can see we can take this common here and the remaining will be some k or a lambda, which is a positive integer. So that means it is divisible by 162. But the crucial part here is this starting step. So once you could able to figure out the starting step and the rest will be easy to do it. Right, so let's move on the next one. So the next application here, applications of binomial theorem is finding the remainder. So we can even use this method of binomial theorem in order to find the remainder also. So let's understand this also by solving an example. So here comes the question, what is the remainder when 5 power 2015 is divisible by 13? So here initially we have to prove that this number is divisible by 13. But now here they have given that by which number we are dividing here, and here we have to find the remainder. So can you guys think of it and give it a try? What will be the starting step? Just have a look, have a thought and let me know. So here what is the number? So it is divisible by 13. So think that so that we could write it nearest to 13. What is the number which is divisible by 5 which is nearest to 13? So think over that way. Or else you can see here it's a even power, odd powered. So try and cover into even or something like that. So initially when it is divisible, we have reduced it in the format of 8k or something like that. But now we have to find the remainder, which means it will be in the format of 13k plus some a here. So where a here is the remainder. Same thing how we have done. So one of the term, try to figure it out such a way that one of the term will become 1. So I'll give you 2 to 3 minutes. So give it a try and let me know if you could able to crack it or not. So let's see how can we convert into 5. So here 5 can be converted here. It should be something in the power. So here we are having an odd power, so we cannot split it. So I'll be rewriting this 5 power 2015 as, I'll just take 1 5 out of it and it will be 5 power 2014. Right? So now what I'll do, I'll take 5 into here 5 square. So 2 into, right? So 5 into 5 square will be 25. That means 25 power 1007. So now here 25 can be, we have to write 25 such a way that we'll be having one of the terms should be 1. Right? That means 5 into 26 minus 1 whole power 1007. It's fine. So from the term 5 power 2015, we have reduced that into the format of 5 into 26 minus 1 power 1007. So now let's just apply our binomial theorem here. So now the term is 5 into 26 minus 1 whole power 1007. So let's just expand this. So let's just expand it, guys. So 5 will be common here. Take it. And then expansion of our binomial 1170 not. So 26 power 1007 and 1 power 0. So it will be plus only. So now it will be minus 1007 C1 26 1006. So minus we have already kept here, plus. So 1007 C2 26 1005 minus, and so on, plus minus it will be going on, and at last it will be a minus here because it's an odd number 1007 26 power 0 here, and this 1 power 1007, so that's why it will be minus here. Right, so let's expand this further. So here 5 into 1007 C0 26 power 1007 here, and the same thing minus here. The only difference we can see here is it's a minus 1 at the last. 100 C1 26 power 1006, and so on here. Instead of here we can write it as minus 1. Right. So here how can we take common here? We have to take 13 common here. Right. So here we are having 26. Here we are having 26. And in the next term we will be having 26. 26 is nothing but multiple of 13. So if we have taken 126 out here, then that 36 can be written as 13. That 26 can be written as 13 into 2. Yes or no? Which means we could able to take 13 common or not? Yes, definitely we could be able to take 13 common. But here, until this before term, we will be having this 26 term, but here there is no 26. To take common here, there should be, so here it's a minus 1. If there is a, if we are having minus 13 here, that means we have added minus 12. Right? So trying to add minus 12 here in order to get 13. And as we are subtracting, we have to add something. So plus 12, but here I am writing outside it. So it will be 5 into 12, 60. So plus 60 at the out. Okay, let me write it this way, so that it won't create any confusion for you. So far what we are having here, it's a minus 1. So apart from this minus 1 term, every term is having 26. That means we can take 13 common. So here in order to take 13 common, I am just subtracting minus 12 and I am just adding 12. Right? So this 12 I'll just take out to the outside. That means 5 into 1007 C naught 26 power 7 minus 1007 C1 26 power 1006. So minus 13 here, and this plus 12 I am just taking it out, then it will be 12 into 5, it will be plus 60. So now from each of the term here I could be able to take 13 common. Then it will be 13k plus 60. Even this 60 can also be divisible by 13. That means 60 can be written as 13k plus 52 plus 8, where 52 is divisible by 13. That means 13, this entire take I am just taking k dash plus 8. That means the remainder here, when we divide this 5 power 2015 by 13, the remainder we will be having here is 8. So this will be the way of solving and finding the remainder while dividing a number with another number using our binomial concept. Right, so let's move on to the next one. So the next one here is finding digits of the number. That means it could be last 2 digits, last 1 digit, last 3 digits. So whatever it could be, based upon the question, we have to find the digits of a given number. So here the question states that find the last 2 digits of the number. So keep it in mind how we have solved the previous two applications, and now I hope you by now you might have got an idea how to start anything related to this application part. So can you guys have a look over this, and can you guys give it a try for this question in order to figure out the last 2 digits of the number, that is 13 power 10. So one thing is clear that amongst 2 digits, 2 terms inside the binomial, one, we'll just try that one of the term can be equal to 1. So that will be our priority here. So here the number we are having here is 13 power 10. So is it possible to write 13 in terms of plus or minus 1? Is it possible? No, right? Then what we can do, we'll just go by this power. That means 13, I'll just write it as 13 square 2 into 5. That means 13 square whole power 5. So what is 13 square? It is equal to 169. So 169 whole power 5. So now is it possible to write 169 in terms of plus or minus 1? Yes, it is possible. So how we can write that? 170 minus 1 whole power 5. So here we are having a tens place here, like a 0 here in the units place, as well as 1, which will be making even easier to solve and find the last 2 digits of the number here. So when we are trying to find this last 2 digits, 3 digits, there is one more condition again, that is one of the number will be 1 and the other will mostly try to be a multiple of 10. Right. So it can be a multiple of 10, 100, it could be anything, but we'll mostly try that in terms of zeros at last, so that we could easily simplify and get the last digits of the given number. So now as we have rewritten our 13 power 10 as 170 minus 1 whole power 5. So let's just do the expansion here. So here the power is 5, which means we'll be having only 6 terms in this expansion. It's the easiest one, guys, because the number of terms will be very, very less here. So let's just do the expansion. 5c naught and then 170 power 5 minus 1 0, so it will be plus, and then here minus 5c1 170 power 4 plus 5c2 170 power 3 minus 5c3 170 power 2 plus 5c4 170 power 1 and then minus 5c5 170 power 0 here. So this will be the expansion, but now here we have to find the last two digits, right? So here you can see 170 power 5, which means we will be having last 5 digits 0, so we can neglect this. And similarly here last 4 digits 0, so we can neglect this. And here last 3 digits 0, so we can neglect this also. Whereas here last 2 digits is 0 here, which means we can neglect this part also. And now here this is 1 digit 0, that means we have to figure out the values of these two. 5 factorial by 4 factorial, 5 minus 4 1 factorial into 170 minus 5c5, that is 5 factorial, 5 factorial, 5 minus 5 0 factorial, 170 power 0, it will be 1, right? So here this will be 5 into 170 minus 1 here. So figure out 5 into 170, 850 here minus 1, that is 849. So here we have to find only the last two digits of this number. So amongst this, what are the last two digits? 49. That means the last two digits of the number 13 power 10 is given by 49. So that's how we'll just, so that's why I mentioned here, if one number will be a multiple of 10, it will be easy to figure out the last digits of the given number. So let's move on to the next one. So here for this question, you have to figure out the last 3 digits. So take it as homework. So far we have done our divisibility test as well as figuring out the last digits and all. So now you are familiar how to start the question and all. So this question you can take it as homework in order to find the last 3 digits here. So the next one here is relation between two numbers. So I hope you have already solved a question related to this relation between two numbers in our previous sessions. But as it will be coming under the application part, so let's have a look over here again. So relation between two numbers. So here there is a question which states that which number is smaller amongst these two. That means amongst 1.01 whole power 10 lakhs or 10,000. So amongst these two numbers, which is the smallest? So we have already done this question, guys. So now I hope you can solve this within minutes. So take 2 to 3 minutes and quickly solve it and let me know the answer. I'll just looking forward to your answers. So one is 10,000 direct and the other is 1.01 whole power. So you have to identify amongst these two numbers which is the smallest one. So we cannot do anything with this. The only thing we could do here is we'll just expand this using our binomial theorem concept. So this 1.01 can be written as 1 plus 0.01. So now let's just expand this. That means C naught. And then 1 power anything will be 1 only here. So 0.01 here will be 0, power 0. And the next plus C1. And then 1 power 1 only. So 0.01 whole power 1. And then C2 0.01 whole square, and so on we can go. So let's figure out the values here. So this one is power 0 and 10,000. So this will be 1 only, plus, so here it is 1, 2 factorial by 1 factorial, and that minus, so it will be 99 lakhs. So that will be getting cancelled, which means it will be remaining with 1 plus 10 lakhs into 0.01. So this will be the second term, and so on we'll be having. So what is this value of 10 lakhs into 0.01? That is nothing but 10,000. So here from the first two terms itself, it is coming to be 10,001. So if we add the remaining terms also, it will be a more value, right? Which means it is obviously greater than 10,000, which means this 1.01 whole power 10 lakhs is greater than the number 10,000. So amongst these two, the smallest number is nothing but 10,000. Right, so amongst these two, the smallest number which is given here is nothing but 10,000. Right, so let's move on to the next one. So that is nothing but the binomial theorem here. So here we are just applying the binomial theorem. So have a look here. I'll just be back. So here we are going to discuss our next concept, that is multinomial theorem. So as I mentioned, we have already discussed this multinomial theorem while discussing the chapter of permutations and combinations also. So let's see here, we are having our binomial theorem, which is nothing but x plus a whole power n. So what is the expansion of this x plus a whole power n? That is nothing but nc naught x power n minus r and so on. So that can be represented as sigma, because it is nothing but the sum. So we can represent this in terms of sigma. So here the binomial theorem x plus a whole power n. So the expansion here in general is nothing but nc naught a power 0, and then nc1 x power n minus 1 a power 1, and so on. So it is nothing but sum which can be represented as sigma. So now this can be written as sigma. So we'll consider this to be r. R will be starting from 0 and it will be ending with n. That means NCR here, x power n minus r, a power r. That means the expansion of our general binomial theorem x plus a whole power n is given by sigma r equal to from 0 to n NCR x power n minus r into a power r. So this can be further simplified and written as NCR can be written as n factorial by r factorial into n minus r factorial. right? And then x power n minus r and then a power r. So now, so here I am having n factorial divided by r factorial. So the same r I am having here a power r, and the same n minus r factorial I am having to be the power of x minus, so power of x. So now I am going to represent my n minus r equal to some s. So now what I am going to take, I am just assuming my n minus r to be s. So now it will be turning out to be sigma from r equal to 0 to n factorial by r factorial. So as I assumed this n minus r to be s, so here in the denominator it will be s factorial. Similarly, the power of x also s a power r. So now from this entire expansion we have simplified it further until x plus a whole power n will be equal to sigma from r equal to 0 to n, that is n factorial divided by r factorial into s factorial into x power s into a power r, right? So this will be our, we have converted our general binomial theorem into a simplified version. So now what we'll do here, so let us consider the expansion x1 plus x2 plus x3 whole power n. So initially what we have considered, it is x1 plus x2, that is x plus a, that can be also considered as x1 plus x2 whole power n, right? So now we are here having another term here. So this can be written as sigma r will be from 0 to n, right? So here nc, so let's take k, 0 to k, nck, that is x1. So what I am doing, I am considering x1 as one term and x2 plus x3 as another term, right? So in the previous one we are having only two terms, so it will be easy to do it. So now as we are having two terms, I am considering x1 as one term and x2 plus x3 as separate term. So now k equal to 0 to n, and it will be x1, first it will be nck x1 n minus k, and then x2 plus x3 whole power k. Yes or no? So this can be written as k equal to 0 to n factorial by k factorial n minus k factorial x1 n minus k x2 plus x3 whole power k. So the similar pattern how we have assumed our previous one. So here also this inside term we can expand it, right? Here we are having two terms, so this is also a binomial, so we can expand it. So n factorial by k factorial n minus k factorial here x1 power n minus k. So now I am taking some p, so sigma p will be from 0 to k, because it is until k, not until n, right? So now it will be k c p, right? So k c p and then x2 power k minus p and then x3 power p, right? So here the concept here is, initially we are having only two terms in the expansion. So now as we are having three terms, I am trying to expand this into three different terms. So it will be sigma k equal to 0 to n factorial by k factorial n minus k factorial x1 whole power n minus k, and the other here sigma from p equal to 0 to k factorial by p factorial k minus p factorial, here x2 whole power k minus p and x3 whole power p, right? So here we are having two terms, one is n minus k and the other is k minus p. So I am assuming n minus k to be r and I am assuming k minus p equal to some q. So now this entire multinomial expansion will be turning out to be sigma k equal to 0 to n factorial by k factorial by r factorial x1 power r. Right, another sigma can also be put together here, sigma p equal to 0 to k, and here k factorial by p factorial, and this is q. So q factorial x2 power q and then x3 power p. So this will be the entire expansion here. Right. So these are the ways. So even if you have 4 terms in the expansion, you can consider. So for suppose x1, x2, x3 and x4. If we are having 4 terms, so what can we do? So we'll consider these two at a time, these two at a time. So we'll just simplify it and then further expand it. So that's how we'll just simplify this multinomial expansion of a given binomial theorem, and it is called to be the multinomial theorem. So in a generalized version, you can see that if we are having some n terms, right, that means x1 plus x2 plus x3 and so on, xk power n. So that will be written as, so this sigma will be from r1 plus r2 plus r3 and so on until k here, because n minus r, n minus k we have assumed to be r, and here it will be n factorial by r factorial into and so on, rk factorial, and here x power r1, x2 power r2, x3 and so on. Right, so this is the generalized term in the given expansion here. So this is the general term in the expansion now. So let's see here the easiest formulas here, that is the number of terms is equal to the number of non-negative integral solutions of the equation. Yes or no? Because here the r1, r2, r3, so these are the values are only positive values, which means they are not a negative integral solution, they will be only positive solution, which means this number of terms can also be rewritten in another way, that is the number of non-negative integral solution of the equation. So what is that equation? r1 plus r2 plus r3 plus and so on rk is equal to n. So the number of non-negative integral solution. So we know, so the number of non-negative integral solution we have learned in our permutations and combinations. So what will be the answer? It will be n plus k minus 1c k minus 1. So these are the number of non-negative integral solution of the given equation. So this one we have already learned in the permutations and combinations. So there is nothing new here. Right. So here as I mentioned, for 3 terms it will be sigma r plus s plus t equal to n2, and here n factorial by r factorial into x factorial into t factorial, so x power that. So if it is 4, it will be n factorial by p factorial into q factorial into and so on. If it is 5, it will be going on like that. If you are having x plus y plus z plus u plus v, which means 5 terms, it will be p plus q plus r plus s plus t equal to n, and then n factorial by p factorial, q factorial, r factorial, s factorial, t factorial, and then x power p, y power, y power q, z power r, u power s, and v power t. So this is how, as the number of terms increases, the following expansion will also be changing according to the number of terms here. So let's do one last question here. So the ratio of the coefficient of x power 15 to the term independent of x here. So you have to find the ratio of 2 terms here in the given following expansion, that is x square plus 2 by x whole power 15. So the ratio here is coefficient of x power 15 and the term independent of x here. So you guys know the general term, the particular term method, so you can apply any of it and let me know the answer quickly. So first write the general term. So tr plus 1 equal to n here 15. So 15c r here, and then x square 15 minus r, 2 by x, r here. Right, so this can be written as 15cr x 30 minus 2r and 2 power r x power minus r. That means 15cr x power 30 minus 2r minus r 2 power r, which means here the power of x here will be in the general term, it is turning out to be 30 minus 3r. Right, so here we have to find the coefficient of this x power 15. That means this power should be equal to 15. Then accordingly, what will be the r value? That means 30 minus 3r should be equal to 15. So 30 minus 15 equal to 3r, which is 15 equal to 3r, and r will be equal to 5. So when r equal to 5, that means sixth term. So the coefficient of x power 15 is nothing but the term that is sixth term here. So we have to find the ratio of sixth term and the independent term. So independent term in the sense this 30 minus 3r should be equal to 0. That means 30 equal to 3r and r equal to 10. So when r equal to 10 in the sense what term it is? 11th term. That means we have to find the ratio of T6 by T11, that is 6th term divided by 11th term, because 6th term is the term where we are having the power of x to be 15 and 11th term is the term where we are having the power of x to be 0. That means the term independent of x here. So now as we have figured out what is the term when we have x, the coefficient of x to be 15 and the coefficient of x to be 0. So now let's just try and find here the ratio of this T6 divided by T11. So the ratio which we have to find is T6 divided by T11. That means 15c5 x square. 15 minus 5 will be 10. Yeah, 15 minus 5 will be 10 here. And then 2 by x whole power 5 divided by 15c 10 here. And then x square whole power 15 minus 10, it will be 5 here. And then 2 by x whole power 10 here. So let's just expand this. So this is when r equal to 5 and this is when r equal to 10. So let's find these values here first. I'll just do here T6 equal to 15 factorial by 5 factorial. 15 minus 5, it will be 10 factorial. So x power 20, 2 power 5 by x power minus 5. That means, so 15 into 14 into 13 into 12 into 11 divided by 5 into 4 into 3 into 2 into 2 power 5. So as we have to find the coefficient only, so the ratio only, so it will be this. Right, or else we'll just try to make it easy. So let's find T6 first. So T6 equal to 15c5 x power 20 and then 2 power 5 x power minus 5 here. That means 15c5 here x power 15 into 2 power 5. Right, so let's go for the 11th term, that is 15c10 and then x square into 5, so it will be 10, so x power 10 here and then 2 power 10 into x power minus 10 here. Right, so this x power minus 10 and plus 10 will get cancelled. We'll be having 15c10 into 2 power 10. Right, so here we have to find the ratio of the coefficient. So here we have to find only the ratio of coefficient. That means T6 coefficient, that is coefficient of x power 15 is 15c5 into 2 power 5 and here 15c10 2 power 10. Right, so this and this 5 terms will get cancelled and 15c5 is nothing but equal to 15c10 because this 15c10 can be written as 15c. 15 minus 10 will be 5 according to the properties related to the combination. That means 15C10 equal to 15C5. So these two terms will be getting cancelled and we are remained with 1 divided by 2 power 5. So 2 power 5 is nothing but 32, which means the ratio here is 1 divided by 32. So the ratio of this coefficient of x power 15, that is T6, is to the term independent of x, that is T11, is equal to 1:13. Right. So this is how we'll be applying our general term and get the answer. So this is one of the previous year's JE question. So that's all for today. I'll just give you some questions to homework. So this question you can work it on for homework. So this is related to the term again. And one more question. So these two questions you can try, take them as homework and give it a try later. So with this, we have finished our chapter of binomial theorem. So we have covered each of the concepts which are related to the binomial theorem as well as the questions related to each of it. So that's all for today. So I hope you're clear with this concept of entire chapter binomial theorem. So once you go through the sessions again, if you have any doubts and any questions that you have to clarify, so please feel free to ask me. I'll just reach out as soon as possible and try to explain you and clear your doubts. So that's all for today, guys. So we'll start a new chapter in our next session. So thank you.